Today, we'll be solving LeetCode 110, Balanced Binary Tree. In this problem, we are given a binary tree and asked to determine if it's height balanced. A tree is considered height balanced if, for every node, the difference in height between its left and right subtrees is not more than 1. Let's look at example 1. We're given a binary tree where the root has two subtrees. When we observe the height of the left and right subtrees at each node, we can see that the difference in height is always 0 or 1. Since no subtree is too deep compared to its sibling, we return true. This means the tree is balanced. Now, how do we solve this? Let's start with the idea. To check whether a binary tree is balanced, we need to know the height of each subtree. So we'll use a technique called depth-first search, or DFS, which visits each node starting from the root and goes all the way down to the leaves. While computing the height of each subtree, we'll also check the difference between the left and right subtree heights. If the difference is more than 1 at any node, the tree is not balanced. To signal this, we'll return -1. If everything checks out and we never return -1, then the tree is balanced. Let's walk through the code step by step. First, we define a helper function inside our main function called DFS. This function takes a node and returns the height of that node's subtree. If the node is null, meaning we've reached the end of a branch, we return 0 because an empty subtree has height 0. Next, we recursively call DFS on the left and right children. This gives us the height of the left and right subtrees. Now comes the key step. If either the left or the right subtree returns -1, that means that subtree is already unbalanced. In that case, we immediately return -1 to stop further checks. Then, we check the height difference. If the absolute difference between the left and right heights is more than 1, we again return -1 because this node is unbalanced. If everything is good, we return 1 plus the maximum of the left and right subtree heights. This one accounts for the current node's height. Back in the main function, we simply call our helper on the root. If it returns -1, we return false, which means the tree is not balanced. Otherwise, we return true. This solution is efficient because it checks each node only once. The time complexity is linear, or O of n, where n is the number of nodes in the tree. The space complexity is O of h, where h is the height of the tree, due to recursion stack space. And that's how you solve LeetCode 110, Balanced Binary Tree. Thank you for watching and let's keep learning.